Right. Now, rule generation, I think what we have discussed is there are many ways that you can actually generate rules. One is you can create the decision tree and then you can convert into a rule set. So that's the straightforward way of doing this. But what we were interested in looking at is covering algorithm. So in covering algorithm, what we do is we start with a particular class in interest, putting the tests so that you try to extract a pure rule set, which is based on the data. So we cover as much as possible for one particular class. So the example we have looked at is like this. So if you look at this simple example, what you notice here is you have two attributes, let's say X and Y, and some data points we have in 2D, assuming that we have numerical data. So we are trying to find rules for classifying it as class A, and you start saying true, which means everything is included. So if you look at the accuracy of this classifier, you can count how many A's. We have 1, 2, 3, 4, 5, 6. We have 6 A's. Total, if you count, you will have around like 20. So this is the accuracy without putting any conditions. So next, what you do is you are going to improve the accuracy by putting some conditions. If you go along the X direction, at some point you can see a point where you can separate A's from B's. So that's what you have seen the next. So for example, in this particular case, what you see is, so we have seen a split point here. And if you put a rule saying that if X is greater than 1.2, this side, which ignores this side, and we say it's class A. So basically we are trying to classify everything as A if the X is greater than 1.2. So if you check here, the how many positives, 1, 2, 3, 4, 5, 6, okay. And the total 7, 8, 9, 10, 11. Okay, this is improved accuracy now with this putting condition. So what happens when you put conditions? We are trying to improve the accuracy, but at the same time, just notice the number of instances goes from 20 to 11. So you decrease the coverage. If you further, you try to refine. So this time you can go along the Y direction and maybe you can find a split point somewhere here. So if that is the case, what will happen? Next time when you put the next condition, right? So this is the situation. So if X is greater than 1.2 and Y is greater than 2.6, that means this area. So if you look at how many records, everything is A, so that is 5. And the total is also 5. So accuracy of the rule is 100%, right? So this is 100% and this is what we have done. So what happens is we have found out our first rule. So we can remove them from the data and then you can repeat the process so that you can find a rule to cover this particular instance, right? So that's for A. Then you go for B as well. So for each class, you repeat this, and that's what we do in covering algorithm. Right. With that said, what we have done is we discuss about how we may work on this. So as we have already seen, we started with generally putting everything into one particular class, adding test, which reduce the cover so that, once you get the pure classification, so that we are going to take it as a rule. So that's what will happen in coverage algorithms. So with that said, we have also discussed the tests. So the test that we have used is simply we calculate the total number of instances and the positive examples, P divided by T, and we finish when this is equal to 1. Right? Or else, if there are any situations that you can split any further, we'll stop at that point. So that's simply how the very simple covering algorithm works. Now, to explain this one, we have observed what we call a data set based on recommending contact lens data. So in this particular data set, let me show you the data set first. Give me a second. This is about recommending three types of what do you call contact lens types based on the four attributes. We have age, we have spectacle prescription, astigmatism, tear production rate. So we have four attributes. So based on the four attributes, we are going to make a decision whether you are going to recommend soft, hard, or none. So that's the problem that we consider here. So the first part for this problem is you have to first decide on a particular class, and you will see we have decided to find rules for hard, right? So that's what you see. And your left-hand side, we make it empty. So empty means we consider everything. So we classify everything as you can see here. We classify everything as hard, right? So I think we should now see the data set to understand how it look like, right? Right now, let me share the data set. Hope you can see. So in this particular data set is about the contact lenses. So these are the age attribute. We have three unique values for each. Then spectacle prescription, astigmatism, and then tear production rate. And this is the recommendation. So you can see we have 24 attributes. So now what we try to do is we try to create a rule set for hard. So we put the empty side for left-hand side and we say hard. So how many hard instances you can calculate? We have one here, right? 2, 3, 4, right? We have 4, right? 1, 2, 3, and 4 instances out of 24. So that will be the accuracy if you just put empty. So now we want to put each and every test. So for example, we can say age young. So how many age young instances here? We have age young, 1, 2, 3, 4, 5, 6, 7, 8. We have 8. Out of 8, how many hard? We have 1 and 2. We have 2. So the accuracy of the rule, if you say, if you put age hard, then the contact lens is hard, the accuracy of this will be 2 out of 8. So that's what we do in this process. So I hope you got the idea what we do. So we possibly go through the data set. We check for all possible tests and we calculate the accuracies. Now I have a question for you. Which test you are going to select out of these data points? So according to what we have agreed in the beginning, we have to select the attribute test, which gives us the best one. So either we can select astigmatism just or tear production rate normal. So one of these would work. So let me go with astigmatism yes. So if that is the case, we know we can update the rule, right? Now we can update the rule saying that if that astigmatism is yes, then the recommendation is hard. The accuracy is 33%. But at the same time, when you say astigmatism yes, the number of rules, number of data points reduced to 12. We started with the 24 in our original data set. Now it's now it's 12 because we have selected astigmatism yes. Now this is a modified data set now. Now we have to search another attribute value, right? Now we have left with 3 other attributes. So we can check for age young, age, and then spectacle prescription and tear rate. So we have to, extend the same procedure. So we'll update our rule. So we put astigmatism yes, and we are looking for another test. Again, the idea is we want to improve the accuracy. So what we need to put is the possible test. Now we have left with 3 attributes. So we will check accuracies for the 3 attributes: age, spectacle prescription, tear production rate. So if you're going back to the data set, if you select age young, we have 4 instances. Out of 4, we have 2 hard instances. Now the accuracy is, 2 out of 4, right? What is the accuracy if it is age pre-presbyopic? So what is the accuracy? If you put the second one, age pre-presbyopic. Yes, you have 4. And how many hard? Just 1, right? 1 out of 4. Presbyopic, again, you have 4. Out of 4, you have 1, right? So if I go through the values, this will be the updated accuracies. Now tell me, right, which one you are going to select now? Okay, we already select astigmatism. Yes, we are looking for the second one to improve the accuracy further. And here are the tests. Which one you are going to select? Okay, good point. Yes, Dilan. Yes, we can select tear production. 2420. Yes, tear production. Why tear production? This will give you 2/3. That means 66% accuracy if you put tear production rate normal. Okay, that means our next step, we put if astigmatism yes and tear production rate is normal, then the recommendation will be hard. Okay, now what has happened? What is the accuracy? It's still 66%. We are trying to improve the accuracy to 100%, right? Remember what we did discuss? Or we can't go any further. So therefore, still we have a rule. But at the same time, you will notice that since we have selected astigmatism and tear production rate values, the data set now refined. Now we end up with only, yes, 6 instances, right? So out of these 6 instances, we have to, see 2 more attributes now we have left. We have to check with age and spectacle prescription. So we'll modify the rule. So we say that if you have estimation yes and tear production rate normal, and we are looking for a possible test out of the 2 attributes. So we have 5 possible combination. So let's try to find the accuracy if you put age young. If you put age young, you can notice that you have a 2. And out of 2, it's hard. So it's 2 out of 2, right? So if you continue, this is the accuracy, right? So now this is what we have. Now can you tell me which one you are going to select? Yes, which one you are going to select? Okay, so if you look at carefully, there are 2 possible solutions. What are the 2 possible attribute value tests? We can go for age young, 100%, 2 out of 2. We can go for spectacle prescription, myope, again 3 out of 3. But which one you are going to select? You have to select one, right? So which one you are going to select? Tilan, select 1, 2. Haratan, select 1. Which one is the best? Is it the first one or is it the 4th one we should select? What is the justification? We should select, fourth one, right? Because it has 3 instances. Okay, we are trying to find a rule which covers, the coverage should be increased. So therefore, based on that, we can go for fourth one. So I will go with the fourth one because I want to increase the coverage, which cover the 3 instances, right? So the final rule will be we cover with the greatest coverage. So that means we'll check the spectacle prescription myo, which gives me 100% accuracy. So the final rule is if astigmatism yes, tear production rate normal, and spectacle prescription myo, then we can recommend that, okay, you should select hard lenses, right? This is just one rule we have developed from the data, right? We originally had 24. This rule covers 3. That means you have remaining 21, right? So you have to repeat the process. So if you have repeated the process, you might get the second rule like this. If age is young, astigmatism yes, and tear production rate normal, then recommendation you have. You see? And you keep on doing to select all the instances which recommends hard. And then you go for the next, right? So these 2 rules will cover the hard lenses, then go for soft, then go for none. So you have to process repeat with other 2 classes. Okay, summary. This, what we have observed, this is called PRISM algorithm. So the algorithm PRISM is to go through each for every class. So you see for each class C, you assign the whole set, the instance set. And then whenever you have instances in class C, you are going to create rows. Whenever you create rows, you start with empty left-hand side. That means you are assigning everything to that particular class, calculating the accuracies, the test accuracy, P divided by T. And every time you are trying to improve the accuracy. So you select the P divided by T, you select which attribute value combination gives you the best answer, and then put it in the rule, right? And then once you finish and we finish with the rule, you remove all the instances which covered by this rule, and then you go to the next one, right? So that's what happened. And this is called, PRISM. Right. So that's about simple rule learning technique. And then there are various different issues that you have to, follow up. So there could be overlapping rules, and there should be sometimes need of a default rule and so on. Right. So just to conclude what we have discussed. So what we have discussed is called separate and conquer algorithm, which means you are trying to identify a rule which covers the many instances in the class, right? And then once you find the rule, you separate out the covered instances. In our example, the first rule covers 3 instances. You have to remove those 3 instances, and then you left with 21. So then you work with the 21 instance as the next step, right? So that's how this works. Any questions? So what I'm going to explain is how to make the implementation, but the rule generation algorithms are not much popular in new implementation. Scikit-learn, for example, you might not see. So I'm going to use a different tool which implements this algorithm, which is called Weka. So the actual Weka interface, maybe I will show you. You can try it out, which you don't need any programming background. It's called Weka. So if you if you find Weka, it's actually Java-based data mining toolkit, where you can actually go to software and go to download, if you want to install in your machine. But let me share with you what I have already installed. So if you open up if you install and if you run Weka, it looks like this. When you open up, it's looked like this. And then if you go to Explorer, then we can view, we can open data sets. Right. So I'm going to open up, the data set, which I have showed you earlier. So I'm going to go to their data folder, program files, Weka 3.8.6, the data. And this is where you have the contact lenses dataset. Right. So everything is just you have to just click it. You can see we have age, spectacle, prescription, astigmatism, TF reduction rate, and this is the class. You can see the class distribution. We have 5 soft instances, 4 hard instances, and then 15 none. If you go to classify, this is where we can develop the classification. So 0R we have already discussed. If you start, it says none, because you have a lot of recommendation as none. And if you choose, let's say trees, maybe, okay, 1R rows. If you click it, it looks like this. It select tier production rate is the best one. If it is reduced, then it suggests none, otherwise soft. Then maybe I can look for decision tree implementation. So if you implement the decision tree structure look like this, right? If you visualize, it look like this, right? And finally, the algorithm I have just described, it comes under rules and it's called Prism, right? And this is the rule set. So you will see it says Prism rules, and you will have a set of rules. Okay, right. So I hope you can get an idea, and if you're interested, you can play around with Weka. There are a couple of videos I have created in my YouTube. You can have a look. Right. But let's see whether we have done it. Yes, wrapper, no issues. Okay, let me implement some, right? Just wait for you. I will give you time for you to down this. So the next one is, now we have the wrapper and everything. Then we have to first check whether the, this is, I told you, the Java based one. I'm going to check with the Java version and also the compiler version. No issues, we can move on. Then we have to open up the virtual machine. So that's what I'm going to do. We are going to open up Java virtual machine. And then that's also no issues in my case. So therefore I can continue, right? Now we need some data sets. The data set has a special format in Weka. So let me brief on this one as well, so that I think it will be added advantage. So the data sets we have to use, maybe I will type the command. The command is, we will say from right, from core converters import loader, and then we load the data set, right? So I'm going to get the data sets here. I will upload it here. So one way to do is I can directly upload and I will share with you the data set with you. So I'm going to go to C. And then I'm going to go to Wake-up folder. I will start with first our weather dataset. So maybe I will select weather nominal. Okay, I have opened it up, uploaded. Right, now it's available. So now we have to load the dataset. And then we will see the commands for this. Right. So we load the converters. We are going to use ARF file. The file name is weather. So I'm going to remove this part. I'm going to put the local one, nominal. I'm going to say the last one is the class and we'll print data. Right, that works well. Right. Maybe we can do up to this point. So let's go one at a time. So maybe I will give you a first command. Okay, if you come up to this point, that means we are ready with our environment. And you can see this is a special data format which is used in Weka, which we call ARFF. And what you see is there's a relation keyword to provide the name for our dataset. It's the dataset name. And here the list of attributes and their data type. So we had Outlook, it's nominal. So these are the three categories. Temperature nominal, these are the three categories. Humidity nominal, these are the two categories. Windy nominal, two categories. And finally our class, two categories. And then this is the data set. Right. So now if you want to use 0R, let me give you the how to build this, the code for this. So you can actually use classifier and you select the classifier class name 0R and you build the classifier and you print it. So that's what we do. And we know from 0R for weather dataset, it says yes, right? So see whether you can get up to this point. Okay, 0R we have discussed, it's called majority classifier. Yes. So if you want to implement 1R, it goes like this. Same thing from the previous, you select the Weka classifiers and you import the classifier method. Within the classifier method, you say the class name is under Weka classifier rules and it's called 1R. You build the model and then you print the model. And if you do that, like what we did in the example, we select Outlook is the best one with the rule set, sunny is no, overcast is yes, and rainy is yes. Right. If you finish up to this point, so let's move on building J48, that is the decision tree classifier, right? And then we build the model and we print the model. Simply, if you do that, this is what you will see. That is textual outcome, right? For the decision tree classifier. I'm going to share this with you, the code. Right. For the visualization, the tree, it's very interesting. You have to get two classes. Sorry, you have to use a library called GraphiViz, which is what we are going to see. So you see a tree structure like this. So let me share the graph as well. Right. So a couple of things that I want to note, like in Weka, this implementation called C4.5. Actually, they say C4.8, the extended version of C4.5. And in Weka, they have used as a J48. That's why we use the term J48 there. And what you have to notice in this decision tree, if you compare the tree structure that we have got earlier, you can see here we have multi-way splits. What do you mean by multi-way? So Outlook, we had three different values. So therefore, we have three branches. This is not available in scikit-learn version because it supports only binary splits. Binary means you have two, right? So this is one of the noticeable differences that you will see if you compare Weka implementation together with the scikit-learn version, right? And here, the other difference is they are using information gain, that is entropy, as the what do you call it, as the measurement to select the root node. So in scikit-learn, it's a default is Gini index. I think we have discussed that. And here they have used entropy or information gain, the other differences. Right, now we'll talk about the prism. Right. Now I think you can understand the differences. You can copy the same thing. So only difference would be the classifier, right? So let's look at the prism. So it should be classifiers. This part we need to change. We have to use rules and then it's called prism. So that's a classifier. And simply you build the classifier using the data and then we'll print. Okay. So we need to, there's a, okay, we have to have this with you. So yeah, let me change. So the problem is, why we got the error here is, so this prism is actually available with another package. So you can notice the error, it says simple education learning schemes. So that you have to have, right? So your classifier should be, so let me change that. So this part should be, right, now it should work. So in the next one, what I'm going to discuss is another machine learning algorithm or the paradigm, which we call instance-based representation. So instance-based representation means that we are not going to create any model as such, what we have seen earlier. So for example, the classifiers like 1R, we got single level decision tree. Decision tree, we have a tree structure. Prism, we had a set of rules. But these are like kind of what we call the concept description, which describe our problem. But this is not the case for all the machine learning algorithm. For example, in instance-based representation, we don't create a model as such. So that's something that we are going to learn here. So this is called root learning. The idea of root learning is instead of you build a model, when you get a new instance, you will see how close that instance to the existing data points. So therefore, this is known as instance-based learning. So how do you know similar? We have to have some function to evaluate the similarity. So for example, in real world example, if you look at a classroom, usually the friends used to sit together. So if I look at a classroom, we normally see a pattern of how you sit together. So when you see a new person comes in, so depending on where he, go, we can identify the particular person. So that's the same idea. So you can define something called similarity, and then based on that, we can predict the label. So one thing to note here is since there's no model building like in trees, this is known as a lazy learning. Why we say lazy learning? Because the learning happens when you get a new instance, when you want to test something. That means the learning we will delay the learning until we got a new instance. So therefore, this is known as lazy learning. Whereas in decision trees, we call it's eager learning, right? What are the methods based on this principle? I'm going to discuss about the nearest neighbor. In simple nearest neighbor, we look for the nearest instance. The other version is called k nearest neighbor, where you look for the k nearest instances, right? So to continue this discussion, the similarity function that we have discussed is very, very important. Usually when we talk about similarity, most common function we use is called the distances. So what we do in the data sets, so we calculate the distance among one point to the other point, right? And when you want to calculate the distances, there are many functions, right? So let's say that you have just one attribute. And let's assume that you have just simple one numerical attribute. So if it is a numerical attribute, you just take the difference, right? It's a simple case. But if you have several, then of course you can look for the geometrical distance. So you can say Euclidean distance. What do you mean by Euclidean distance? You get the difference, square them for each of these attributes, and then you finally get the square root of it, right? But what if you have nominal attributes, like let's say outlook is sunny, outlook is overcast, outlook is rainy. They just label, right? So if you have labels, right, what you can do is you can check whether the labels are the same. If they're same, the distance is 0. If they're different, the distance is maximum. Let me say 1, right? So that's how you handle the distances. Another thing that you need to think about when you work with nearest neighbor like algorithm is whether all the attributes are equally important. So what you can do is, if you think that some of the attributes are more important than the others, then you can give more weights for the important ones. So that's the idea. Okay, so going back again, distance calculations. You can use a Euclidean distance. You calculate the difference between all the attributes, square them, and finally you get the square root. And in the city block or Manhattan, you just take the absolute value. So these are the two common, distance measures. This is also available as Minkowski distance, and I will explain this in the implementation in scikit-learn as well. When you select nearest neighbor, for example, right? In Minkowski, if you select P is 1, that means this becomes 1, this becomes 1. This is the absolute values, right? You simply sum up the absolute value. So that is Manhattan or city block distance. If you put P is 2, then you get the difference, square them, and then you get the square root, which represent the Euclidean distance. So same thing, right? But P could be any value, right? So that means if you select like different value for P, then you get different distance function. Okay, let's try to understand the two distance functions. So let's say I have 4 attributes, and then let's say these are the attribute values, right? Can you calculate the distances? So this is known as dissimilarity matrices. So basically, you will see the calculation of distance from one point to all the other points. So similar to that, let's say if you want to work it as a classification problem, so this is how it will happen. So what happens? So you have class information as well. So let me put, let's say this is class, and let's say x1 is plus, x2 is minus, x3 is plus, this is minus. So let's say these are the class labels. So this is assuming that we have classes also given. So that means we have positive, this is negative, this is negative. Let's say we have a new data point. So let's say this is my new data point. So what is the class? Is it positive or is it negative? So we don't know the class label. Can you tell me? Yes. So just by visually looking at, you can say it's positive, assuming that this is the closest, right? But you can calculate the distances. Sometimes it's not difficult. This is only 2D and that you can do. So ideally what you do in nearest neighbor, you calculate the distance from the test instance for all the other instances. So you calculate the distance here, calculate the distance, and you calculate the distance from here, all the 4. And select if it is one nearest neighbor, 1KNN. Sorry, so 1NN. What do you mean by 1NN? Or simple nearest neighbor will get the class label. So the new instance is in attribute x is 2, y is 3. So this is what? And we don't know the class. So if you're using single nearest neighbor, maybe we can say plus. What about if the k is 3? What do you mean by k? So you look at the 3 closest instances, right? So you have to calculate the distances. But assuming that if you have plus and 2 minuses, right? Let's say this is the closest, these are the next 2 closest cases. If that is the case, if you use k is 3, then this might say minus. You have to check. I didn't check this. But just by visually looking at, assuming that these 2 are closest to here, these 3, x1, x2, x3, and if you look at the majority, then it will be minus. So hope now you understood how nearest neighbor works. So in nearest neighbor, you can notice that in this particular example, these instances are themselves the model. So what happens when you get the new instance? We don't know the label. So we calculate the distances, and depend on whatever the value we have chosen, we get the instance label. So if you look at the nearest instance, it will be plus. If you look at like 3 nearest instances, assuming that these 2 are the closest, then you go with the majority and then you will get minus. Right. I think I explained how exactly nearest neighbor works. So ideally, you don't need to install, or you don't need to store all the instances. Only representative one will be enough in that particular case. So these are called prototypes. Right. So that's about how nearest neighbor works. Now, there are a few things we have to understand, right? Now, if you use nearest neighbor like attributes, so nearest neighbor like classifier, the attribute is influencing the decision because you are calculating the distances. So let's say that one attribute scale is different from the other attribute scale. There's a significant difference. So the larger the difference, then the higher the influence. So therefore, ideally, if you are using nearest neighbor like algorithm, you need to normalize. What do you mean by normalization? That means you have to pre-process your data so that they are in the same interval. So you can define min-max, or you can say between 0 and 1, whatever it is, right? So that you have to do. So if you are using different numeric, and they are measured in different intervals, as a first step, you need to optimize it. Sorry, you have to normalize it. So there are 2 ways of normalizing this given to you. First technique is you can subtract the minimum and divide by max and min, so that this will be between 0 and 1. Or else the other one is you can subtract the mean value and then you can divide by the standard deviation. So both can be used to normalize the data. The distance for nominal, like I said, outlook is sunny, rainy, and overcast. Yes, of course, the distance is either 0 and 1. So 0 means they are same labels. 1 is the labels are different. Last one, for common policy for missing values. So if you have missing values, then we can assume that the distance are maximum, right? Maximally distance given the normalized attribute. So that's what we can think of. Right. So let's finish our discussion of a nearest neighbor classifier. So this is very simple idea. Most of the time you get accurate result, but this will be very, very slow. Why it is very slow? Remember, I told you, like when you get a new instance, you have to calculate the distance from that instance to all the other instances. So assume that you have a very large data set. Think about the number of calculations that you have to perform to find out, right? So therefore, you have to go through the entire training data. And if you have a very big data set, this takes time. It's very, very slow, right? But if you look at implementation, there are some existing solutions to handle this when you have situation like this. So usually, although we say that nearest neighbor like one have no structure, but you can use KD tree or ball tree for the data representation. So you can efficiently represent data. Second point, as I told you earlier, we'll assume that all the attributes are equally important. And if you know that some attributes are important, more important than the other one, you can use simple weights. Right. The noisy instances. So most of the time you can use one nearest neighbor, but when it is you are not getting the accurate results, so maybe you can increase the K, and then you can go for majority vote, right? Or if you see that you are getting errors because of particular instances, they are known as noisy instances, and you can remove them. Okay, so that's all about the nearest neighbor classifier. Any question from that? Okay, so I'm going to talk about another basic machine learning algorithm. Now, this is called, actually, we are going to talk about naive-Bayes classifier, basically based on statistical modeling. We simply calculate the statistics based on the data. That means we calculate set of probabilities, and then these probabilities are the model, right? So what I'm trying to say here is in 1R, we had a single level decision tree. In tree structure, we have tree structure. In rule set, we have a rule. And then in previous one, nearest neighbor, we have used instances themselves. In statistical modeling, basically, we have a set of probabilities. And let's see how we can use these probabilities calculated based on the data set can be used to make prediction, right? So that's what we are going to do. So this is also called opposite of 1R, because in 1R, we select just one attribute, and this is opposite. You are going to use all the attributes. And what you're going to do is we will base on two assumptions. The first assumption is we assume that all the attributes are equally important. And then second one, we will say they are statistically independent. So why we are saying this? Because you will see later on the probabilities we calculating by multiplying each of the individual probabilities. So for that, statistical independence is needed. But if you look at actually a real data set, you don't see this, right? Not all the attributes are equally important and they are not independent of each other, right? But still, you get very accurate outcome in most of the cases. The point is, if you can, assign the probability to the right class, although you have some issues in the accuracy, you still be able to get decent accuracy with naive-Bayes classifiers. Right. Now, going back to naive-Bayes, so we assume that everything is independent each other, and I said it's violated in practically it's not the case, but still we are getting the accuracy. So as far as we provide the maximum probability the correct class, then we can get the accurate classification. Right, now let me explain this with the data set. So what we do, I hope you remember our weather data set. If you remember the outlook attribute, outlook for sunny, we have 2 yeses and 3 nos. Outlook for overcast, we have 4 yeses and 0 nos. And outlook for rainy, we have 3 yeses and 2 nos. So we calculate the probabilities of being classified as yes for sunny, because we know that being sunny, we have 2 instances. Yes, we have 9 instances. So we say there's a probability of 2 out of 9. When outlook is sunny, the day is being classified as yes. So similar to that, for no as well, we can calculate the probability. So what it says is, so given the outlook is sunny, probability of classifying that particular instance as no is 3 out of 5, because we have 3 here for sunny, and that is 5. So these are the probabilities, and simply this is what you do. So basically, we calculate the probability values based on the data set, and you get a set of probability values. Right. Now, these are called sometimes prior probabilities. I will come to that point. Now, let's say we have a new weather data point. Let's say outlook is sunny, temperature is cool, humidity is high, wind is true. What is play? So that's what we need to understand. So we can calculate based on these probabilities. So this is how we do. So this is the problem. We have given that outlook is sunny, temperature is cool, humidity is high, and wind is true. And we need to find out what plays. So this is what we need to do, right? So the values are outlook is sunny, temperature is cool, humidity is high, wind is true, and we need to identify the play. So this is what we do. We calculate the probability. Now look for sunny. So sunny for yes. Let me use green color for sunny. Yes. So we calculate the probabilities. What is the probability of outlook sunny? So outlook sunny is 2 out of 9. So we have 2 out of 9. And then temperature cool. Temperature is cool. The yes probability is 3 out of 9. Right? Then humidity is high. Humidity is high. 3 out of 9. Wind is true. Wind is true. 3 out of 9. So this is what we have. And finally, proportionally, we know play yes is 9 out of 40. So we have an independent assumption. So when you have prior probabilities can multiply each other. So you multiply them each other. Right? So this is for yes. Right. Similar to that, we can work out for no as well. So what is no? When outlook is sunny, it's 3 out of 5. Then temperature is cool, then 1 out of 5. Then humidity is high, 4 out of 5. Right? Windy is true. We have 3 out of 5. Finally, we have 5 out of 14. Right? So you have to work on this, and this is what you do. And when you do this, what you will notice, right? What you will notice is the values that you are getting from here, it will not be added to 1, right? So for example, in my previous case, if you calculate the values, right? What are the values you are getting? Can you check? 0.206. And for this is 0.0053. So we are getting some true probabilities like this. So these are not probability values, because if they are probabilities, this will be added to 1. So therefore, you have to normalize, right? So what we do here, like I hope you got the idea. So given this data set, right, we calculate the values. They are not probabilities. So they are called likelihood values. So if they have probabilities, they would have added to 1. And then we normalize. By normalizing, what we means, we divide this number by the addition of these two. And then when you calculate, these will be the probabilities. Okay, I have a quick question. Now, given this day and given these probabilities, are you going to play the game or not? We are not going to play the game, right? Chatrika correctly mentioned, we are not going to play because it says 80%, right? Probability 0.8 means 80% of the time we are not going to play, which means 20% of the chance to play the game, right? There's a possibility, but majority is for no, not to play the game, right? So if you compare our previous algorithm, this is slightly different. So we have probability, uncertainty about the classes. So trees always said yes and no. Rules always said yes and no. But here it says there's a percentage. So there are 80% probability for classifying it as no. Right. Now, if I will go on to mathematical basis, this is based on Bayes rule. In Bayes rule, what we are going to do is, given the evidence, that means in this one, given the attribute values, we need to identify the classifying being yes or no, right? The hypothesis is what we need to identify. So in our case, we have to determine whether it's yes and no. So determining yes and no, provided that particular attribute value combination, this is what we need to do. So what we know is, given that the hypothesis is yes, the probabilities. And since the naive assumption, right, we can actually multiply them together. So calculation of these are known as prior probabilities. And then what we need to calculate is what you call posterior probability. Right. Now, assuming that these attributes are independent each other, then we can multiply. So that's what we are going to do. So if graphically shows you this, it's like this. We have evidence, and what we are trying to find out is probability of classifying this particular evidence as yes. So again, we have to calculate the probability. So if you put up in the equation, it look like this, and we don't know the evidence of the probability. And we don't need either, because if you calculate the same for positive and negative classes, and by following the normalization that we have discussed, this part cancels out. So it will be the same calculations that we have observed earlier as well. Right. Any questions? Right. Now, what about this day? Can you take down this one? Then I'll go back to the probability values. I want you to try to calculate the probabilities, follow the same things that we have seen earlier. Can you take down this? So it says outlook is overcast, right? Temperature is cool, right? Wind is true. Sorry, humidity is high, wind is true. What is play? So let's go back. Calculate the probabilities like this. So what we need to now identify is, we have outlook is overcast. Then temperature is cool. Humidity is high. Then windy, D is true. The question is, are we going to play or not? Play, we don't know. We need to find out. So what is the likelihood for yes? What is the likelihood? Outlook is overcast, that is 4 by 9, into temperature cool, that is 3 by 9, into humidity is high, 3 by 9. Then windy true, 3 by 9. For no, okay, now this is the problem. We have 0 divided by 5. We have cool, 1 divided by 5. Humidity, that is high, 4 by 5. Windy true, we have 3 divided by 5. So these are the attribute value. The problem here, if you notice, that this is 0. We are calculating probabilities. Yes, like we can calculate, but no, we can't, right? Because this will be 0. So you can notice. So when you have a situation like this part will be 0. Now we have a bit of a problem, right? We can't calculate this because then the probability for no will be 0. So how do you handle this? This is where we have a problem of 0 probabilities, and this is known as 0 frequency problem in Naive Bayes. So what do you mean by 0 frequency problem? That some of the attributes counts are 0, then the probabilities become 0, and when you multiply, then the whole probability becomes 0, which is we have a bit of problem. So how do you handle this? The idea is you can add 1 to every attribute value combination. This is called Laplace estimator, and then we can work on the problem. So let's go back. So how do you handle this? So this is how we have. So you have add 1. So what do you mean by add 1? So you add 1 here. So simply you will get, right? So this side we have a bit of problem. We have a 0 here. We will add 1 here. 1. This is also 1. This is also 1. So what happens, the probabilities? So this becomes 4, and this becomes 8. And this becomes 1, this becomes 8. This becomes 3, right? This becomes 8. So the probabilities are adjusted so that we don't have 0 frequency problem. Right. Going back to the next one. So now we have understood how do you handle this. This is what we call Laplace estimator. Right. Now, having said that, right, then what happens, your probabilities will never be 0 because you can handle those. Next, very interesting question. So now we have learned how to handle that situation, but what about if you have missing values? So outlook is missing, for example. Let's say you have outlook is missing. You have value only for temperature cool, humidity and the wind is true. So what is play? Right? What is play? So can you think of a way of handling this one? Handle one way to handle missing values, since we don't know the value here, we can just ignore this one. And we have probabilities for temperature, humidity, and windy. So just you ignore the outlook and you can take the remaining attributes. Yes. So that's one way to, handle or work with missing values, right? So still you can calculate the likelihood value. So you just get the values from the previous one, get the likelihood values, normalize them, and then you get probability values. So I think we now discuss about how do you work with problems that you encounter, zero frequency problem and the missing values. One last thing I would like to discuss, how do you handle numerical one, right? So for example, let's say you have numerical data. So how do you handle this, right? So one of the problem is how do you calculate the probabilities given that you have numbers, numerical data. So for that, what you can do is you can use, what you call the density functions, right? So in numeric attributes, what we do, we'll assume that attributes have a normal or Gaussian probability distribution. So if you look at the implementation in scikit-learn, you have Gaussian naive Bayes. You don't have a classifier called naive Bayes. You say Gaussian naive Bayes. They're assuming that you use Gaussian probability distribution. So what is Gaussian probability distribution? So you can define the probability density function based on the mean value. Mean meaning like you add all the values together, divide by the number of points, and then you calculate the standard deviation. Put it into this equation will give you what we call the density functions. So given the weather data set, assuming that you have numerical data, you will find mean and standard deviation for each of the classes. And then for a given value, or let's say we want to calculate the probability values when the temperature is 66, we will put in the equation. So you can use it here, that it's 1 over square root of 2.5 sigma. And then we have the value, subtract the mean, divide by sigma square. So if you apply this, you will get the value. So this is what we call density function. It's not probabilities, but you can treat them as probability. Similar to that, for the humidity also, you have calculate the values. Now, when you want to calculate the everything, you can replace this. So for example, if you have a situation like this, so these are the probabilities from the data set, and these two, we use density functions to calculate. And then again, the probability values. And when you multiply them, you get a values and normalize, then you get probability values. So now if you refer this one, you will notice that the 80% of the time you are not going to play, 20% time you are going to play the game. Right. So let's finish our discussion on naive Bayes. So what I told you in the beginning is there are a couple of assumptions in naive Bayes. So the two assumptions that we have discussed is they are equal and then they are independent, right? Equally important and independent each other. So reality is the different, but still we are getting decent accuracy, right? So, but there will be many issues if you have too many redundant attributes or identical attributes, right? If your numeric attributes are normally distributed, then you can use other kernel density estimates. And we have observed that we can use Gaussian to calculate the likelihood values, and then later you can convert into probability values. Right. I think that's enough for today's class. What we need to discuss next is I will discuss how to implement I want to discuss implementation details for covering algorithm. We couldn't finish it today. Then nearest neighbor, then the naive Bayes. And hopefully I can discuss how you may actually compare multiple algorithms. Right, that's